Well, good evening, everyone, and thank you for joining us this evening. This is the final talk of 2021. I'm going out with a bit of a bang tonight because we've got one of our very own who's going to be our guest speaker. So for those who don't know me, my name is Wendy and I work for the Science and Technology Facilities Council, or STFC. I'm going to show you a picture of where I work. This is Daresbury Laboratory, based in the Northwest, and it's one of a number of sites for STFC. So for those who don't actually know who we are, STFC is one of Europe's largest research organisations. We enable the UK's natural sciences, together with the computing and engineering communities, to carry out their world-leading research. And we do this by working with universities, national laboratories, regional campuses, and scientific facilities right across the UK and abroad. We study a whole range of science, from the smallest particles that we know of, right through to objects in outer space and the mysteries of our universe. So we're really fortunate at STFC because we have quite a number of sites across the UK. So I'll just give you a very quick overview of them. Down in the bottom right, we have the Rutherford Appleton Laboratory in Oxfordshire, which is our largest site and covers research in particle physics, scientific computing, laser development, and space science. Chilbolton, right at the bottom there in Hampshire, is much smaller, carries out research in atmospheric science, radio communications, and astronomy. Polaris House in Swindon is the STFC headquarters. Daresbury Laboratory in Cheshire, where we're hosting the event from tonight, is internationally recognised for its work in nuclear physics, high-performance computing, and accelerator science and technology. One of our prettiest sites is based in Edinburgh and is the UK Centre of Excellence for Ground and Space-Based Astronomy. And that's where Carolyn, our guest speaker tonight, is working from. And finally, we have an amazing site near Whitby on the northeast coast, 1.1 kilometres underground at the bottom of a working potash mine, studying science in a really unique environment. So as you can see, we are well represented across the UK, and we love to talk about science, and that's why we have Talking Science, so we can tell you a little bit more about what we do. So tonight's speaker, Dr. Carolyn Atkins, is a research scientist at the UK Astronomy Technology Centre in Edinburgh, which I've just shown you, exploring how to create mirrors for telescopes using 3D printing. Carolyn has built her research career in the field of lightweight mirrors for space-based telescopes and has been fortunate to live in England, Wales, Scotland, and the US while exploring this field. We definitely need to get you over to Ireland at some point, Carolyn. So thank you very much. And without further ado, I will hand over to Carolyn. Thank you.
Great. Hello, everyone. I'm just going to share my screen. So hopefully you can all see my screen.
Yes, thank you.
Great. Fantastic. Right. Hello, everyone. My name is Carolyn Atkins. I'm a research scientist, as Wendy says, at the UK Astronomy Technology Centre, and delighted to have you with me tonight so that I can talk to you all about lightweight, and specifically about lightweight mirrors. And I'm now going to basically break down my title because I realised it was a little bit obscure, a bit abstract, to explain why I chose this title. So I'm first going to talk about light. And I'm going to talk about light in terms of the electromagnetic spectrum, going from gamma rays all the way to radio waves. And I'm particularly going to be talking about light in terms of light coming from astronomical objects going into a telescope so that we can analyze the light and so the astronomers can do their job. I'm going to talk about weight. So I'm going to talk about mass, and I'm going to talk about weight in terms of space-based telescopes as well. And the next thing I want to talk about is the combination of these two things, how to make something that is lightweight. And by lightweight, I mean low mass. And this is particularly important. I'm going to be talking about this particularly in regards to lightweight mirrors. I'm also going to make a little segue and talk about wasps, because these are brilliant engineers, and I really want to share with you kind of what they do and how they create lightweight structures. And then what I'm going to try and do, hopefully at the end, is you're going to see how lightweight structures and mirrors come together to put mirrors in space and how they can then go forward and link to space telescopes in the future. So to do this, I'm hoping during the talk that we're going to answer these 3 questions together. So the first question is, why do we have telescopes in space? The second is, why do we need lightweight mirrors? And the third is, what is 3D printing? So what is 3D printing is a little bit maybe a bit of a curveball in this one, but this is really about what my research is about how to create mirrors using 3D printing. So before I ask that very first question, I kind of want to make a little bit of a pit stop, because I'm going to be talking about mirrors a lot, and I'm going to talk about a primary mirror a lot. And I basically just want to make sure that we're all on the same page about what I mean by a primary mirror. So primary mirror is the largest mirror in a telescope system. It is the first mirror that the light sees when it comes from the astronomical source. So it is, in my opinion, most important mirror. And because it is the first mirror that the light sees, the larger of a mirror, the more photons from your source you can collect. So the more information you can get from your source. And these are basically examples of the primary mirrors. So they are the first mirror in the system that the light touches. So now moving on to our questions. Why do we have telescopes in space? So I've got a question for you all, which hopefully will be coming up on the screen thanks to Phil. And the question is, why do we put telescopes in space? And I'd like you just to kind of select any that you think are true. And the options are: the Earth's atmosphere blurs the image. It's easier to build really big telescopes for space. It lets us see different wavelengths of light. And you can see more of the sky from space. So feel free to select any that you think are true. And I'll let Phil tell me when there's enough all voted.
Thanks, Caroline. Right, we've had nobody participated so far, so I'm worried slightly that something's not quite worked with the poll. I'm going to relaunch the poll for everybody and see if this works. It's now working. Okay, I think we've had enough responses. I'll end the poll now for you, Carolyn.
Fantastic.
I'm sharing the results.
Okay, that's kind of what I expected. That's an interesting kind of split. Okay, yeah, so most of you kind of decided that the Earth's atmosphere and the wavelengths of light. So we're going to go through each one of these in turn. So the Earth's atmosphere blurs the image. That is true. And that was clearly evident by how many people agreed with that one. So essentially what we have is the Earth. And around the Earth, we obviously have the atmosphere. This is very good for us humans because obviously we like to breathe and we need the atmosphere to do that. Unfortunately for astronomy, it is less conducive. So if we have a telescope on the ground, it needs to look through the atmosphere to look at the astronomical source. And this creates blurry images. This is because the atmosphere is like in continual motion. It has multiple layers to it, all moving in different directions. This has the effect to kind of blur the light coming from the astronomical source. And this is essentially the reason why stars twinkle at night. Why they twinkle is because of the atmosphere disrupting the light. It's also kind of analogous if you've ever been in a swimming pool and you're wearing your goggles and you're underwater and you're kind of looking up maybe at your friend or at the ceiling or something else. And somebody maybe kicks some water near you and it kind of then blurs your image again. So that's kind of what I mean by this turbulent environment, is that this kind of continuous motion of these kind of gases which kind of blurs out the image. So to give you kind of a better example of how this actually works in reality, so this is an example of a tadpole feature within the Karina Nebula. And this was taken on a 4-meter diameter mirror in Chile. And as you can tell, there's like a black blob in the center and a little white one just a bit to the right of it. And it's a bit blurry and you can't really see very much. So we do the same image using Hubble. All of a sudden we get a lot more information. And I will accept the criticism that the pixels are much smaller in this image. But we also don't have the atmosphere, which is kind of blurring a lot of the information out. And what I would also really like to point out in this is the fact that the Hubble Space Telescope has a significantly smaller diameter mirror than that of the Blanco telescope. So we're collecting less photons, but because we don't have the atmosphere disrupting where those photons are going, we get a much cleaner image. So my next question was, it's easier to build really big telescopes for space. So a few of you actually said yes to this. And you would think so, because you're obviously putting James Webb in, that's going up very soon. But unfortunately, no, this is not true. Any engineer who has to work on a space telescope has many challenges to face. One of the biggest challenges with space-based telescopes is the fact that once they go up, you can't really change anything. Hubble was actually an anomaly in that fact, the fact that it was actually built to be serviced. It's incredibly expensive to service a telescope, so that tends not to be where we're going to be going in the future. So if you create a telescope like the James Webb, which is going up in a few weeks, it has to work first time. Okay, so the next question. So a lot of you also thought this one was true, and you are of course correct. So again, if we look at the atmosphere, what this atmosphere does is it blocks certain wavelengths of light. So it allows us to see, obviously when we look to the night sky, we can see the stars, which are kind of emitting in the visible wavelength, and we can see that because that can transmit through the Earth's atmosphere. But the atmosphere actually stops things like gamma rays, X-rays, and the infrared. And this is actually very good for us because we obviously don't want to be irradiated by gamma rays or X-rays. But it's not too good for astronomy if you actually want to look to see what's happening. So here's another example here's a better example of a previous figure, which shows the electromagnetic spectrum going from gamma rays to radio waves and what can penetrate the Earth's atmosphere. And what you can see is gamma rays and X-rays and ultraviolet pretty much are all absorbed by the Earth's atmosphere. So is the infrared and the microwave. And then there is two windows, one called the optical window, which is visible light, a little bit of UV and a little bit of infrared. And then you also have a radio window. And this is why we have radio telescopes and optical telescopes on the ground, and why we have to have telescopes such as for X-ray and infrared in space. So I guess the question is there anything actually to see at those wavelengths? And hopefully you will agree there's a resounding yes. So this is the Whirlpool galaxy viewed in 5 different wavelengths. So this is radio, infrared, optical, UV, and X-ray. And what these different wavelengths are looking at are different temperatures. So the radio is looking at very cold gas, and the X-ray is looking at very hot gas. And hopefully what you can see is that each image of a different wavelength is giving you a different description of what is happening. So obviously it's not just galaxies, this happens with nebula as well. And this is actually my personal favorite example. This is the Crab Nebula. And I think this is a brilliant example of the strength of multi-wavelength astronomy. So for example, if you compare the X-ray image with that of the visible or the radio, all of a sudden you have a whole different description of what is happening within this astronomical source. And this is really the power of multi-wavelength astronomy. Now we're looking a little bit closer to home, we have the sun. So obviously from the Earth's surface, if we look up to the sun, which is obviously not advisable, but if we look and we see it, you get the optical image, which is, I'm going to say it, pretty dull. Few sunspots, other than that, pretty dull. But as soon as you start looking at the infrared, the UV, and the X-ray, what looks quite a dull surface all of a sudden becomes really dynamic, and you can be able to understand that more information is going on, and there's definitely a very dynamic environment to it. And even a bit more closer to home, we have Jupiter. So this is a picture of Jupiter in the infrared, visible, UV, and X-ray. And again, it's just giving you a different story to what is actually happening within this environment. And I particularly like the X-ray because I am very biased towards X-ray because my background is in X-ray. But in this case, the X-ray is showing the aurora on Jupiter. So it's definitely showing, building a story about this source, this astronomical source. So yes, very much it allows us to see different wavelengths of light. So the final question, which was, you can see more of the sky from space. So from the poll, a few of you thought this was true. It wasn't quite as resounding as the answers 1 and 3. And the answer is yes, but. So the question is, you can see more of the sky from space. So this is a map of a Hubble Space Telescope of all the sources that it has seen. So this shows the Northern Hemisphere and the Southern Hemisphere. And as you can see, it's actually sampled a lot of the sky. And typically, telescopes in orbit can see more of the sky than a ground-based equivalent. But you don't need to be in space to see all the sky. We obviously have ground-based telescopes, and we have ground-based telescopes in every continent in the world. And this allows us to see the whole night sky. And you could definitely argue that it is significantly cheaper to have ground-based telescopes than it is to have space-based telescopes. So the answer was yes, you can see more of the sky with a space-based telescope, but you don't need them to see that. So kind of as a conclusion, the kind of key reasons why I put telescopes into space is the fact that it removes the blur and it allows you to see more of the spectrum. So I'm going to be a little bit flippant now and say, why don't we put all telescopes in space? So why don't we get something like the ELT, bundle it in a rocket and launch it off to space? Very quick answer is, it's very, very expensive. So how much does it cost to launch 1 kilogram of sugar into space? So I just kind of want us to think about how much it typically costs. So say the astronauts on the ISS want some sugar in their tea. How much is it going to cost to launch that one bag of sugar into space? And the value you typically come out with is between 10,000 and 5,000 pounds to launch that kilogram of sugar. And it's very much dependent on which launcher you use. But I think you can agree that's quite expensive for a cup of tea. So to kind of conclude this little section, the main reasons we put telescopes into space is because it removes the blur, it gives us more access to the spectrum, but it does cost a lot of money. So I feel we've probably answered this question now. So let's move on to, why do we need lightweight mirrors? So first I want to kind of define what a lightweight mirror is. So this very terrible drawing, on the top section I have 2 mirrors. I have the front surface, which is reflective, and I have the back surface. And what happens with a lightweight mirror is that material is removed from the back side of the mirror. So once you've removed that material, you get something which is a little bit like that. And because you remove mass, your mirror becomes lighter. So that's what a lightweight mirror is. So my next question, which hopefully Phil will put on the screen for me, is why do we need lightweight mirrors? So I've got 3 options here. One is cost. They are cheaper to launch. Number 2 is lightweight mirrors are better at reflecting light. And number 3 is they have structural benefits. And what I mean by structural benefits are they're kind of maybe more rigid, or they have some structural engineering qualities that makes them more beneficial to use.
Okay, Carolyn, people are frantically pressing buttons and voting at the moment, so the numbers are going up. I'll give it another few seconds before I close the poll for you. So here we go. Yep, it's stabilized. People have got an answer. So here are the results now.
Okay, cool. Excellent. I wasn't quite sure what we were going to get through this one. So the majority of you have all said that they are cheaper to launch, which I would hope so, because we've just been talking about how much it costs to launch. Some said better reflecting light. Others have said structural benefits. Okay, cool. So let's go through each one of these as well. So resounding success, yes, they are all cheaper to launch. Because you reduce the mass, you reduce the cost of what it's going to cost them to launch. But there's always a however. So but my yes but here is they are more expensive to make, and they are, so it's definitely a trade-off between the expense in fabrication versus the expense in launch. I'd probably say that it's probably you're going to get your money's worth if you make a lightweight mirror. So you probably are going to save money on your launch, but they are more expensive to make and they are more difficult to make. So also your lead time, the time taken to make that mirror is going to be longer. Okay, so the next one, lightweight mirrors are better at reflecting light. So I was quite pleased that majority of people said that this was wrong, or they didn't think this was true. And that is correct. And so here's just a little sketch of kind of what I wanted to show. So on the left-hand side is a solid mirror, and on the right-hand side is a lightweight mirror. And here you have light incoming. So for a solid mirror, when you fabricate it, when you make it, you polish it, you are going to get a much better surface quality from your mirror than you do for a lightweighted mirror. That's because your mirror thickness is going to be incredibly uniform, which means you'll get this very good surface. So be able to reflect your light to the point where it needs to be very accurately. Because a lightweight mirror, in contrast, doesn't have a uniform thickness, it is obviously very non-uniform. When you polish this, it's going to create ripples on the surface. And this is going to have the effect of disrupting where your reflected light goes. So it's making it more likely that you'll get a poorer quality mirror. I say more likely, you can still get very good lightweight mirrors, but it's going to be more likely that they will be less good in comparison to their solid counterparts. So in my next question was, they have structural benefits. And again, this is a yes, but I've also done a yes, but again, as you can tell, there's never just a yes answer. And I said, but predominantly for larger applications. So when it comes to mirrors, there tends to be a golden ratio, and that is that you want the diameter of your mirror to be 6 times the thickness. And essentially the reason why you want this is because if you go any thinner, so you have a thickness that is less than that, your mirror is more prone to deformations. So it's more floppy and more flexible, and which will mean that it'd be more difficult to manufacture, more difficult to mount. If you make it thicker, you don't really get any benefit in deformation, but you just make a much heavier mirror, which is then more difficult to maneuver and with all the kind of mounting mechanisms around it. And a lot of this kind of the 6-to-1 ratio is actually driven by gravity, which kind of obviously is affecting how you manufacture things. So I feel that maybe some of you might be thinking, but you're talking about putting mirrors into space. Why are you worrying about gravity? But ultimately, at the moment, we have to make all our mirrors on Earth. So they are going to be prone to gravity-induced manufacturing errors or problems. So as I mentioned earlier, this is particularly the case when you consider very large mirrors. And in this case, I want to give the example of the Giant Magellan Telescope. So this is a 30-meter diameter mirror. So hopefully you can see there are 7 mirror segments in this. So if you go from the tip of one segment to the tip of the opposite one, that is going to be around 30 meters. So each segment itself is 8.4 meters in diameter. When you get to this side, you really need to lightweight otherwise your mirror gets incredibly heavy. And this is actually a ground-based example. So I kind of want to show you, I really want to show you this telescope mirror because they are absolutely amazing. So this is the back of, the 8.4 meter telescope mirror. So this is the light weighting you can see. So each of these holes is the entrance of a little open cavity inside. And this is what an 8.4 meter lightweight mirror looks like. It's huge. And when I was mentioning earlier the kind of technical challenges, when you have mirrors that big, they become a very challenging object to move around and to handle. So by lightweighting them, you're removing the mass and you're making them easier to move around and transport on the Earth's surface. And I think there are some very amazing videos and pictures of these mirrors being fabricated. And if any of you have time at the end of the talk, I thoroughly recommend taking a look at some of these videos because they are absolutely amazing. So why do we need lightweight mirrors? So the cost, yes, they are much cheaper to launch, and they do have significant structural benefits, especially when you're getting towards the larger mirrors. They are just more easier to handle. So now I'm going to move on to talk about, I kind of want us to think about the real difference between a solid mirror and a lightweight one in terms of both cost and kind of mainly cost. So this is kind of what the images we saw earlier. And on the left, you can see from the ground-based telescope, and on the right, you can see from the Hubble. So now I kind of want us to think about those primary mirrors again. So the primary mirror for the ground-based telescope, that was a solid mirror, and it is basically 50,000 kilograms, and it was made in the 60s. In contrast, the Hubble Space Telescope is a lightweight mirror, and it has a smaller diameter, and it was made in the 80s. And I think the key things I really want you to take away from this little comparison is the fact that the ground-based telescope has 19 times the mass than the Hubble, but only 3 times the area. So I'd say that's not a great trade-off. So what I kind of wanted to do is kind of just to kind of do a bit of mental arithmetic to kind of see how much it would cost to launch these into space. So I'm saying calculators out, but I mean, you probably could do this in your head or on your phone. So what I want us to think about is a Blanco 4 meter primary mirror, and considering the mass of that and the cost it's going to take to launch that into space, how much that's going to cost essentially. So I've kind of put a nominal value of 4,500 pounds, UK pounds per kilogram. So I'm working on the assumption that we're going to launch on a SpaceX Falcon 9. And so I just kind of want to think about how much it will cost in each case. And essentially what the numbers come out to be around 70 million pounds to launch that Blanco 4 meter primary mirror. Whereas it will obviously be 19 times less to launch the equivalent Hubble mirror. So if I'm working at ESA or NASA and I have to choose how I'm spending taxpayers' money, I know which one I'm going to approve. I'm going to approve the one which is cheaper and has a slightly smaller area. So on the next slide, I really want to show you how Hubble made such a lightweight mirror. So this is the Hubble Space Telescope primary mirror. And as I mentioned, it was made in the early 80s. And this is a lightweight mirror, which is called a sandwich structure. So instead of having material removed from the backside, what we actually have here is a top plate, a honeycomb center, and a base plate. And these are all kind of glued together to create the mirror. So this is how that mirror is significantly lighter than the ground-based one. So obviously this was made in the 80s. Is this still relevant today? And yes, it is. So I'm hoping that many of you will have been hearing about the James Webb Space Telescope in the news. So James Webb is you can imagine it to be almost a successor to the Hubble Space Telescope. and it has a diameter of about 6.4 meters, I believe, and it, significantly larger diameter mirror. And hopefully, if I don't jinx this by saying it out loud, it will launch on the 22nd of December this year. And what I really want to show you now is what each of these hexagons look like on the back. So James Webb isn't just one solid mirror, it's actually made of several hexagons tessellated together. And this is what the backside of the hexagons look like. So essentially, there's lots of triangular prism pockets that have been removed from the backside of the mirror. And this is an example of a open back lightweight structure. So this is how James Webb keeps its weight down for its primary mirror. And just as a quick comparison between the Hubble Space Telescope and the James Webb Space Telescope, you can see that the collecting area of the James Webb is about 6 times that of a Hubble, but actually the mirror mass is less than Hubble. So that is achieved by the fact that it has a lower density material. It uses beryllium instead of glass. But it's also because if we look at the last slide again, because the mirrors are smaller in diameter, they can have a smaller thickness and still remain rigid by being single mirrors. So that is another way that it reduces weight. So hopefully I've now convinced you that we do need lightweight mirrors, that they save you weight, they are better for structural rigidity. And now I kind of want to describe 3D printing and what 3D printing has to do with mirrors and what it has to do with wasps and why I really want to talk about wasps today. So what do wasps have to do with it? So in my opinion, wasps are amazing engineers. And many of you may have seen a wasp nest. I actually haven't, but I've only seen photos of them. But this is what a wasp nest looks like. It's basically made of paper, so it's incredibly lightweight, has incredibly low mass because it's made of paper and very thin layers. And the wasps actually build this layer on layer. So this is what the outside looks like. And this is what the inside looks like. So hopefully what you can see is it's a very intricate design that the wasps can make. And it's essentially made out of paper, so it's incredibly lightweight. But as you can probably see from that internal structure, it's a load of hexagons again. And these hexagons are quite a rigid structure. So we take another look at this. You can see the outside and the inside and how these kind of fit together. So the inside hexagonal part is kind of protected by this kind of outside thin layers of essentially paper. And why I think this is so amazing is the fact that the outside structure, these thin layers of paper actually act as thermal insulation. So it's basically like wearing a jumper. Whereas the little hexagon areas, that's essentially where the wasps grow and start as small wasps and kind of grow. So it's kind of more of a habitation. So the thermal insulation actually keeps the habitat of where the wasps are kind of growing at a correct temperature. And I think this is just a very good example of how brilliant nature is at engineering and the innovative structures you can create when you have a lot of design freedom. And so why am I telling you this? So why was I so excited when I learned about this a few months ago? So wasps build these structures by chewing wood, mixing it with their saliva, and then building their nests layer by layer. And this is such an incredibly similar approach to 3D printing. So this is kind of the reason why I show you this is I kind of want to highlight the fact that what we can do with 3D printing maybe going forward. So this is a wasp nest. So what you can see here is the queen going from the left to the right. So from the left, you can see the queen wasp, I believe, starting the nest. And then over time it evolves. Then more worker wasps get made and they kind of start building outside layers. And this is so similar to 3D printing, where you start you start with a structure and you just build it layer upon layer. And this allows you to create structures that you could not create easily via conventional machining. So I think you could all kind of agree maybe that the wasp nest on the top could not be created via using a mill or a drill or a lathe in one piece. You can maybe make it in sections and stick it together, but not in a one piece. And the same goes with additive manufacture. You can't create structures like that from one piece. So the other reason I wanted to kind of talk about Wasp Nest was the fact that it's such an engineering feat. It really is. It's kind of, a big achievement of what can be done. So by using this layer upon layer approach, and that's kind of what we want to achieve with 3D printing. So my next question is, what materials can you 3D print? So, and with this question, I kind of want you to think about kind of what different things you can print today. So Phil, if you don't mind sharing the poll.
Yep, that's launching now. Okay, so lots of thought. Our people are now pressing buttons. They've got the hang of this. Okay, lots of answers coming through at the moment. Okay. Okay, still quite a few people answering, and that's now slowed down. Okay, I'll end the poll and share the results.
Oh, interesting. Okay, so chocolate, metals, ceramics. Okay, less confident on the moon dust, but very confident on ceramics. It's interesting. Okay, fantastic. Thanks, Phil. So what materials can you 3D print? Let's start with chocolate. Yes, you can 3D print chocolate. Hurrah. I'm questioning why, but you can. And people do in the catering business, especially if you want to create very bespoke chocolate decorations. It's actually quite challenging to do because you have to keep the chocolate at a certain temperature. And obviously things have to be incredibly clean, but yes, you can 3D print chocolate. So let's talk about metals. Again, you're all pretty confident about metals, and quite rightly so. You can 3D print metals. And this is pretty common now, and there's lots of different ways you can print metal. So the example picture is one method, but I'll be showing you a second method as well later on. And you're all very confident about ceramics as well, which I was very surprised about. And yes, you can 3D print ceramics. Actually, ceramics are one of the hardest ones to print. It is incredibly difficult to print ceramics, and you are very limited in materials that you can print with at the moment. But yes, you can print ceramics. And moon dust. I was so hoping you were all going to say yes, but I was surprised that not many people said yes to this one. But yes, you can, and it's so exciting. So moon dust is being looked at to be printed with at NASA and ESA. And the idea is that when we eventually go to the moon and we want to build a little moon habitation, we can take the moon's regolith and actually use that as a printing compound to build these habitations. And for me, this is just spectacular. If I could get a job helping print this moon base, I absolutely would. It is amazing. So what I really wanted to highlight with this question was the fact that 3D printing is no longer just about plastics. It's no longer just about your desktop printers creating little plastic models. You really can print in a large variety of different materials. So this all leads very nicely onto my research. So what I do as my day job is I look at how we can use 3D printing to create lightweight mirrors. So the design challenge, which I've kind of demonstrated with the Hubble Space Telescope and the James Webb Space Telescope, is to create lighter, more rigid mirrors. And I want to do this using 3D printing as a tool and using the innovative design and kind of a more organic way of thinking, which comes from a layer upon layer approach. And this is all looking towards making something new or a new type of mirror for future space telescopes. So why 3D printing? I mean, I kind of have explained this already, but the key is really to kind of create structures that would not be possible via traditional machining. And hopefully what you can see by these structures I'm presenting here are not something you could easily get a drill or a mill or to make conventionally. So these are things that you can only create via 3D printing. So we kind of want to look at how we can use these designs to create our mirror structures. And to give you an idea of like how I want to do this, so the design phase is looking at how we can create new designs. So it's a case of how we can implement this innovative design, which 3D printing will allow, into our production of mirrors. I'm also looking to create these mirrors in metal. So I mentioned this earlier in one of the slides, and I'm now going to show an example of what metal printing looks like and how I'm using metal printing. So what you can see here is a video of metal 3D printing, and this is a powder process. So what you can see here is a layer of metal powder. In this case, it's aluminium powder, and the lasers are coming in and fusing that aluminium powder together and to the layer below to create a 3D structure. And once it's finished the layer, it then deposits another layer of powder on top, and then the lasers come in again. So this is how you kind of create a metal structure layer by layer. And then my next video is showing you how do you basically remove that object from the metal powder. So the previous example was aluminium, this is now titanium. And what my colleague is doing here is she's excavating the three mirrors from that aluminium powder. So the new designs are enabled by the 3D printing, and I'm looking at using metal printing to create the mirror substrates. And then what I'll be doing is I'll be looking to use polishing and diamond turning, so very traditional methods, very conventional methods to generate the reflective mirror surface. And this is all looking at new telescopes in the future. So hopefully that's given you a bit of flavor of my research. So what I'm really interested in is the design challenge of lighter, more rigid mirrors using 3D printing as a tool and making something new. So to conclude today, hopefully you've got a flavor for what 3D printing is and how it can be used to create lightweight mirrors and why lightweight mirrors are important. So hopefully you'll come away today with a greater feeling for the answers to these three questions. So why we have telescopes in space, why we need lightweight mirrors, and how I'm using 3D printing to create those lightweight mirrors. And with that, I thank you for your attention and I welcome any questions.
Thank you so much, Carolyn. That was absolutely awesome. Such a beautifully put together presentation. This is a lesson in space science. It's also a good lesson in how to put a good presentation together as well. We have got a number of questions, so I'll just get through them as quick as I can because we're getting up to 1:45 now. So Tony was the first one that wrote in, asking a couple of questions about Webb actually. How much gold has been used to coat the mirror of the James Webb Telescope? Actually, I think his first question before that actually was, the James Webb Space Telescope is coated with gold. Why was gold chosen rather than any other element? And then he followed on to say how much gold was used.
Okay, I should have anticipated James Webb questions, but I didn't. So gold is chosen because of the wavelengths that you're reflecting, that you want to reflect. So James Webb is an infrared telescope, so it's reflecting light, infrared light. And what you find is if you do a graph, which is reflectivity in one axis and you have wavelength along the other, what you find is that different elements, so gold, silver, iridium, aluminium, they will have a different curve, a different rate of reflectivity at different wavelengths. So what gold is very good at, gold is very reflective. So it means it is more likely to reflect 100% of the radiation that falls on it at infrared wavelengths than it is at other wavelengths. So for example, aluminium is not very good, I believe, at reflecting at infrared wavelengths, which is why it's not used. So that's why gold's used. In terms of how much gold was deposited, I can't answer that question very well, but in terms of a thickness of deposit, so in terms of how much gold has been deposited upon those mirrors, it'll be of the order of maybe 10 to 100 nanometers. It's on the kind of nanometer scale. You don't need a lot of gold, or you don't need a lot of mirrors, a lot of the reflective coating to reflect the instant light. So you only need a very thin layer. So we're talking probably nanometer, tens of nanometer thickness kind of layer. I'm sorry, I'm not an expert on James Webb, but hopefully that's answered your question.
It's such a good question. In actual fact, one of the Webb UK talks that's been on recently over the autumn, this question did come up, and the answer was, it's almost like the gold has just been sprayed, because it literally is nanometers deep. And if you rolled all the gold that was on the mirrors, it would be the size of a marble in size. And that really drove the answer home. It's such a small amount, because in actual fact, the mirrors are made of beryllium. Is that right?
Yeah, the key core component of the mirrors are actually beryllium, just because it's very light and it's very good material, a very stable material to make mirrors in. Unfortunately, it is very toxic as well. So it's actually a very dangerous material to work in to create mirrors. But yes, they obviously have processes to do that, which are safe.
Very interesting. Okay, so we'll go on to Mary Jane. Surely there is a trade-off with lightweight mirrors depending on what they are being used for. You wouldn't use one if the purpose of what it is doing couldn't be fulfilled.
Absolutely. I mean, it's all very dependent on your mirror requirements. No, absolutely. I mean, if all you want to do is, if you want to create a telescope for your garden or something like that, for like a small amateur observatory, you don't need to create a lightweight mirror. In fact, it probably will cost you a lot more money, and there's no reason to do it. But if you're considering mirrors in space, there are definite advantages on creating lightweight mirrors, even if you don't need to worry about things like mass. That's because nowadays you really have to consider things like the design for demise. And what that means is, when you send a telescope or you send anything up into space, you have to have a plan for how it's going to end its life. And why that's so important for mirrors, or like telescope mirrors, is the fact that if you have, say, a dinner plate size piece of ceramic in space, and you need to design that to burn up in the Earth's atmosphere, because obviously we're trying to mitigate how much space junk we have orbiting the Earth, then you need to make sure that that will burn up in the atmosphere. And unfortunately, ceramics are notoriously bad at burning up in the atmosphere. In fact, they are designed not to. So some of you may remember the shuttles, and they had ceramic tiles on the front of the shuttle to kind of as a heat resistant. So they're very resistant to burning up in the atmosphere. So it's definitely a trade-off of what application you are trying to use. I mean, you wouldn't go to the expense of creating lightweight mirrors for everything, but in certain applications they are required, and you would need to make them.
That's a really comprehensive answer. Thank you for that. It's got me thinking about the film Gravity now. I need to watch that again. John is asking, would a thin back layer not help the rigidity of a lightweight mirror?
Could you repeat the question again, please? Sorry.
Would a thin back layer not help the rigidity of a lightweight mirror?
Absolutely. So in the two examples I showed the Hubble Space Telescope and the James Webb. And in the Hubble Space Telescope, you have what's called a sandwich mirror. So you have a top plate, a honeycomb center, and a base plate. And you basically bond that all together to create your mirror. And that's actually a much stiffer mirror than if you just remove material from the back. However, unfortunately, it's also they are a lot more difficult to make, and they're a lot more difficult to make well. So you have a benefit that you can create lighter, more rigid mirrors via that method, but they do tend to be poorer quality, and they also tend to be more expensive to make. So which route you go, whether you go open back or if you go sandwich, is very much kind of a balance between how much money you have ultimately and how light you need to make your mirror. If you don't have very tight weight requirements, then you probably would go with open back because it's easier to make. But if you need the lightest possible mirror and you have a lot of money you can throw at it, then yes, a sandwich mirror is be the better option, which is what you're describing with the base plate on the back.
I was thinking it should be called a waffle mirror rather than a slide mirror. That's all I could see was a waffle making machine. Edward W is asking, can you 3D print in space?
You can actually 3D print on the ISS already. They've been doing that for a number of years now. So initially they were printing little plastic parts, but they're now looking at how to print in metal, because obviously printing in metal is going to be slightly more useful for certain applications. One of the biggest challenges of 3D printing in space is things like gravity. Obviously, you're not going to have necessarily a gravity vector, so your prints are going to be less stable to a degree, but it's absolutely what people are looking at moving forward. So I know they're already looking at how to put a metal printer on the ISS and how that functions in zero-G. And I think long-term, people are thinking about how we can print larger structures in space. So I think it's very much a case of, let's see where the next few years takes us.
Yeah, sending the codes up for the printing rather than people up to print is something, isn't it? Gillian is asking, if you can 3D print with moon dust, could you launch a 3D printer into space and print the back structure of a mirror with the moon dust and stick it on a lightweight mirror surface? This is really blue sky thinking, but isn't this what science is? We need to push that.
Yeah, no, I mean,
question is a silly question.
No, not at all. So yeah, I mean, absolutely. I mean, I'm very interested in following this moon printing of habitations, because there's definitely the argument for, if you send up the printer into space, you print like a basic structure with moon regolith, then you can look to, how can we process that regolith to create different types of mirrors, because you don't necessarily need perfect mirrors for every different wavelength. So you could create a mirror that is slightly less good for optical, but is very good for infrared. Let me backtrack once slightly. So you want to create a mirror. If you want to create a mirror for X-ray, and that's a very, very short wavelengths, you need to create a mirror that is very, very highly accurate. That's because you're dealing with very, very small wavelengths. Conversely, the reason why you have things like the Dreadful bank, which is a very large dish, it's not very accurate, it tends to look pretty rusty and things like that, is because you have very long wavelengths. So it's a lot more, a radio telescope is a lot more able to accommodate manufacturing defects in the optical surface. So what you could see perhaps in the future is using the moon regolith to create, maybe not mirrors for optical astronomy, but you could definitely make them for the longer wavelengths potentially. And I think what the person was asking was, could you use the moon regolith to create a backing structure? And I don't see why not. I mean, if you're creating things on the moon, you actually, and then you're launching them into space, you actually have less gravity to work against, so your launch costs will be down as well. I would say blue sky thinking, it's how we need to move forward as well. So it's not a silly question.
There you go, Gillian. You need to get a job at STFC. Come and help us. Anna was asking, could you make a mirror like the Hubble mirror, but using metal aerogel for the honeycomb middle? It's strong and it's very lightweight.
I'm less familiar with metal aerogels. I think you're talking about creating kind of a lightweight kind of fine lattice with metal, if that's what I understand. Yeah, I mean, that's kind of what we're potentially looking at doing with 3D printing, is how to create these kind of very lattice structures with 3D printing to create the lightweight kind of sandwich mirror style. I would say that the challenge of creating something like Hubble at the moment is literally the technology available. So most of the mirrors I'm working on for my personal research at the moment tend to be the size of a coffee cup in diameter, so relatively small. And that's because they are easier to print, and as soon as you start scaling up, the facilities that you need to use are less. There aren't many facilities available to use which can print very huge mirrors or very huge structures at the moment with the accuracy that you need. So I think ultimately we have to wait till the technology kind of catches up with what our ambitions to a degree. But yeah, I mean, I think ultimately what we would hope to do is to create a structure that is light, as light as Hubble, if not lighter. And basically to use the kind of innovative design that 3D printing gives you to look at how we can reduce the weight and kind of make a more innovative design ultimately. So as I say, I'm less familiar with the aerogels, but if it's talking about creating lightweight metal structures to replace the kind of the honeycomb structure and the other structures, then yeah, I think it's probably possible in the future, but I would say not quite today.
Yeah, we've had some aerogel back at the lab in a science kit that we've had, and it's the strangest material to hold in your hand. You can't actually feel it. It's just quite bizarre, really. I've got two more questions.
Okay.
One from Jane C. If you replaced a mirror in a compact, now I don't know whether this means a compact mirror, like a makeup mirror, with a lightweight mirror, how thick would it be? I think this is to try and get scale potentially. So it's scaling down from a large telescope mirror to a small mirror, like
so
handheld size maybe.
Yeah, so if we're talking about a mirror in your kind of a compact, like say for your makeup or whatever. So with something like that, say it's 6 centimeter, ultimately it depends on how accurate you need that mirror to be. If it's just a mirror to look at yourself, then you can get away with quite a few optical distortions. Where if you want to create a mirror that size to look at something very accurately, so you want to put it in a telescope system and it needs to look and it needs to reflect the light very accurately, then you probably want to put tighter constraints on it. So what I mean by that is the mirror in your compact, you can create that quite thin, and typically the glass in a compact will be a couple of millimeters thick, because the mirror accuracy doesn't need to be very good, because when you're looking at it through your eyes aren't that good either. Whereas if you want to actually do science analysis with a mirror, you're going to want it to be a lot more precise, which is when you're going to want it to be a slightly thicker mirror in itself. So it all very much depends on the application and what your requirements are. So I hope that answers your question.
Yeah, I think it demonstrates the multi sort of faceted side of this research that you do, and so many things to consider along the way. And the final question isn't really a question about the subject matter, but it's a bit of fun. Who's your favourite Big Bang Theory character and why? Do you even have one? Put you on the spot there, haven't we?
Yeah, rather.
You may need to think about that one.
Yeah.
That's a bit mean, wasn't it?
I would probably say Amy. I'd probably say Amy.
Amy.
Yeah.
I don't know who Amy is. I'm going to have to go and research that now. Anyway, on that note, thank you so much. It has been really interesting. We've been talking about the James Webb with schools and the public for a long time. With my colleague Gemma, we go out on the road and we get people online and we talk about this thing. And we talk about the mirrors a lot and how beautiful they are and how difficult they've been to make and everything. But actually, I'm kind of thinking in a different way with it now. I really feel like we need to turn the thing around and look at the back of it, because we've never really talked about that side of it. It's always about how beautiful the gold looks, and that's its trademark symbol. So you have actually brought quite a different dimension to the science. So thank you so much for that. And it's great to hear firsthand from somebody like yourself who's actually working on the coalface with this kind of research. So I'd just like to thank the public for joining us tonight. It's our last talk of the year. Thank you for supporting us. We couldn't run these talks if we didn't have an audience. And it's really hard to communicate these talks to the general public because there's very few routes we can get the information out. So if you can tell your friends and family and people that you meet about these talks and spread the word, you do us a great service. We also love your feedback. So, you know, any evaluation that you can fill in afterwards on our online form. We do read through every single one of them and we scrutinise them. So thank you so much to Paz for doing it. And all that's left for me to say is have a safe Christmas, have a happy Christmas. We'll pick up again in the new year with our first talk in 2022. It's around about the 26th of January. And we've got another one of our own, Chris Pearson, who's going to be talking about the life of an atom. So that's another exciting one to bookmark for that date. So in the meantime, I'd like to thank you once again for joining us. I'd like to thank Phil and Gemma in the background. We've had IT problems all along the way, but we always get there in the end. And actually, Phil was hilarious before when he was doing the polls, because I was just thinking about the Eurovision Song Contest when the results were coming in. Great compare. So thank you so much, everyone, for your support, and we'll see you in the new year. Thank you.